Let's start with the simplest question. How do we find the internal energy of gas particles? Here we have a container filled with ideal monatomic gas particles. The question is, how are we supposed to find the total kinetic energy of the gas particles? Since in an ideal gas, the particles are assumed to behave in almost the same way, we can just find the kinetic energy of one particle and multiply with the total number of particles inside it. Let's do just that then. We are going to simplify our simulation and start with just one particle. And instead of moving in all dimensions, let's restrain it to move in only the x direction. When the particle starts moving, it is going to have a velocity negative v of x, assuming leftwards is the negative direction. And it is going to travel a distance L before hitting the wall and returning to its original position. Of course, after it hits the wall, the particle will now travel in a velocity of v of x, assuming the momentum is conserved. We know that the change of momentum is the final momentum minus the initial momentum, which is mvx minus by negative mvx. And after doing some simple algebra, it gives us 2mvx. Now let's say that the time taken for the particle to complete this movement is t, and we know that the particle had traveled a total distance of 2L with the speed of vx. Hence, t equals to 2L over vx. The reason why we want to find the change in momentum and time is because now we can calculate the force exerted by the particle onto the wall by using the formula F equals mvx divided by t, which is equal to mvx squared divided by L after doing some simplification. We now have the force, but what about the pressure? We know that pressure is F over A, whereby F is the force exerted by the particle onto the wall of the container, and A is the area of the particle in contact with the wall. We can substitute the values into our formula and get that P is mvx squared over V, where V is the area times the length, or the volume occupied by the particle throughout this movement. Rearranging the equation, we get PV equals mvx squared. But that's just for one particle. In an ideal situation, we will have many gas particles, so the total pressure will be the sum of all the pressures, or as illustrated here. We can actually do a mathematical trick here, which is to multiply the right-hand side by n over n, where n is the total number of gas molecules in the container, to get the equation PV total equals m times n times the average velocity of the gas particles in the x direction. But we know that the gas particle is not only going to move in the x direction, as it has 3 degrees of freedom: x-axis, y-axis, and z-axis. In fact, from geometry, we know that the actual velocity for the gas particle is given by this equation: v squared equals v of x squared plus v of y squared plus v of z squared. Now, if you think about it, there's absolutely no reason for v of x to be greater than or less than v of y or v of z. There's no reason why nature would favor one dimension over the others. So, in an ideal situation, v of x will be exactly equal to v of y and v of z. Using that, we can get the equation v squared equals 3 times v of x squared, and therefore v of x squared equals v squared divided by 3. Substituting this into our original equation and letting PV equal nRT, we get our new equation. nRT equals the mass of a gas particle times the total number of gas particles times 1/3 of the average velocity of the particle. Here, we can use yet another mathematical trick, which is to divide both sides by 2. The reason for this is that now we have an expression for the total kinetic energy. 1/2 mv squared times the total number of gas particles is just the total kinetic energy of the gas particles. Rewriting this, we get our final equation. The total kinetic energy of monatomic gases equals 3 over 2 times the number of moles of the gas particles, times R, times the temperature of the container.